Welcome, everyone. Sorry about that. We're just a little bit late here, but I wanted to welcome you to the webinar today. Thank you for joining us. This is the second of a series of 3 webinars this summer from the Waste to Wisdom project. Today's webinar is focused on the life cycle assessment and economics of biochar from forest residues. My name is Tom Waddell. I work with Craig Rawlings at Forest Business Network, and our company is a partner in the Waste to Wisdom project, one of 15 regional partners, and our company is in charge of outreach. I know many of you read our newsletter, might very well have seen it advertised in the newsletter, so thanks again for joining us. Now, before we move into the presentations, we have some really great presentations today. Before we do that, I thought I'd address some of the housekeeping issues. If you're having any technical problems, audio issues, there's a chat box to the right on the right sidebar. Please feel free to send out a message. You can send it to me directly, the host, or to everyone, whatever you like, and I'll do my best to help you. Now, a common problem that I've seen, not many people have it, but if you're having audio problems, try logging out of the webinar and then coming back into the webinar. Most of the time, that fixes that issue. Now, if you have any questions about the presentations today, there's a Q&A box right there on the right side as well. And my suggestion is that if it is a question to the presenters about the content, please do put it in the Q&A box instead of the chat box, although you're welcome to do both, whatever works best for you. Now, this webinar is being recorded today, so if you lose an audio connection or you don't have time to listen to the entire webinar, we will record it. We'll have it posted on the Waste to Wisdom website within a day or two, and it will be on the webinars page of the site, and actually it's going to be right on the same page that you registered for this very webinar. But I'm going to send you a reminder when that webinar is posted, and you'll be able to go back and review all the material and see all that content again if you like. All right, without further ado, I think we're going to move into the presentations. Up first is Deborah Page Dumrose, and she's going to be our first presenter. We're very excited. So Debbie, give me just a few seconds, and I'm going to move the mic over to you, and then you can get started.
Hello, everyone. Welcome to the webinar today, and as Tom mentioned, it's focused on the life cycle assessment and economics of biochar. This webinar is the second in a series of 3 webinars held this year under the Waste to Wisdom project. Like Tom said, my name is Debbie Page Dumrose, and I'm a research soil scientist with the Rocky Mountain Research Station in Moscow, Idaho. Today I'm going to give you a brief introduction about the Waste to Wisdom project and a little bit about biochar before letting my colleagues Ted Bielik from the Forest Products Lab and Maureen Putman from Woodlife Environmental Consultants deliver information about life cycle assessments and economics. At the end of the presentation, Hans Saphan will moderate a question and answer session. If you have questions or comments, as Tom mentioned, please put them in the Q&A box at the right-hand side of your screen, and please select the option to direct the question to all panelists so that we could all see your questions. The webinar presents results from the Waste to Wisdom project. It's a $5.8 million project that was funded by the Department of Energy and led by a team of researchers from universities, the Forest Service, private companies, and 3 biomass conversion technology partners. Let's start by describing the motivation for this project. The Waste to Wisdom project is investigating methods to make valuable bioenergy and bio-based products such as torrefied wood, biochar, and briquettes using forest residues. Forest residues are an immense and underutilized resource, and transportation costs have been prohibitively expensive due to their low bulk density and market value. Overcoming this economic barrier to harvest forest residuals requires increasing the efficiency of transportation or increasing the value of the residuals before transportation. Our project has researched converting forest residues into bioenergy or bio-based products, including densified biomass briquettes, torrefied biomass, and biochar. The project has 3 main focus areas. First, Dr. Hansa Pan led a group to research innovative methods to harvest forest residuals to develop high-quality feedstocks with low moisture and ash content. Secondly, the Schatz Energy Research Center partnered with industrial equipment manufacturers to understand how biomass conversion technologies can process forest residues to produce these products. And finally, using the data generated from the previous tasks, economic analyses and environmental life cycle assessments were conducted to determine the economic and environmental benefits of these systems. This webinar will focus on the results of the economic and environmental assessments of biochar that were produced as part of this project. The outline of today's webinar is to continue this brief background and provide information about the characteristics and uses and benefits of biochar. Once I'm finished, Maureen will provide results on the life cycle assessment, and Tad will discuss the economics of biochar, and then we'll follow with the question and answer section. So, biochar, why are we interested in biochar? I got interested in working with biochar because of all of the overstocked forests, particularly in the western United States, and the millions of acres of beetle-killed forests in Canada and the United States. The longer fire season and increasing fire severity, those of you in Montana will appreciate that, and the windows to do prescribed burning have been narrowed. And so we end up with a lot of forest residues on many of our sites. And so the question is, what do you do with it, and how can we bring some value to this non-merchantable wood? So current forest land management looks at doing forest restoration, and mostly using thinning and salvage logging. And it's an easy and quick fix to pile that excess woody biomass, reduce the fire risk, and burn those piles. But as a soil scientist, one of my main concerns has been that oftentimes these piles are burned in the fall when soil moisture is low, and we can have long-term impacts. And there are many slash piles around the West, scars left from slash piles that today still show that there's no forest regeneration, and so this is one of our main concerns. The other concern is that oftentimes bioenergy harvesting could degrade long-term productivity. One of our concerns has been evaluating the sustainability of these, and it hasn't never shown in the western United States that this has been a long-term problem, except for on soils that are extremely sensitive to harvest operations. But one of the ways that we can remediate some of these concerns is to use biochar to replace carbon that's removed during harvesting, and we can improve soil conditions to lessen drought or nutrient stress. So one of the things that I've focused quite a bit of my research on has been that adding biochar to many sites, forest sites, range sites, and mine land sites, does several things. One is that it decreases the wildfire risk because that wood that would be left on site has now been taken care of. We also believe that because we're changing the water relationships in the soil, that we can decrease the risk of insects and diseases. We sequester carbon by adding a carbon product to the soil. I hope that in the future we can use this as part of the carbon credit program. And one of the things that biochar does is that it decreases greenhouse gas emissions. So this is a quick summary of the role of biochar, but one of the main things that we've found is that biochar is one way to provide value to this unmerchantable material and allow us to do something with it besides burning it in slash piles. We found from our research that we can increase tree growth by between 5 and 20% more. We can certainly restore many areas that have been degraded, skid trails, log landings, road beds, mine sites, and most of that is because we alter water relations within the soil and change organic matter content. This leads to long-term resiliency in our forest sites, improved infiltration, and makes the soil more resilient to flooding and drought. And so that's my summary, and at this time I'm going to turn it over to Maureen, who will talk about the life cycle assessment. So hold on one second while we switch the microphone.
Well, good morning or good afternoon to some of you. Yes, my part of the presentation will be the life cycle assessment of biochar. I am presenting this data and worked on the LCA model specifically, but it does not go without credit to others. Elaine O'Neill also worked on the forestry model that I was able to input directly into the LCA model, and quite a bit of the data for the biochar production came from the Schatz Energy Center, Mark and David down there. So it's a team effort. So my task in the life cycle assessment of biochar was to really determine the environmental impacts associated with producing biochar. And within that, we wanted to look at, is there a relationship between biochar quality and feedstock quality and the type and amount of impact that we were able, or that the results presented. In addition to that, there was some discussion early on about comparing different biochar production systems, but for the simplicity of today's presentation, I am just going to present the results from what's called the BSI system, or the Biochar Systems Inc. Biochar production machine. So within the LCA of biochar, what are we really looking at? What environmental impacts do we consider in the LCA? And probably the main one and the driving force is always energy consumption. And based on the type of energy or fuel you use and the amount of energy, you have different emissions that are generated. And those emissions contribute to different impact categories like global warming potential, ozone depletion, or smog. These are just a few. And again, today for the presentation, for the simplicity and the time that we're allowed, I'm only going to present results for the global warming potential. A little bit about the LCA methodology. Really the key component in a life cycle assessment is what we call the life cycle inventory, or LCI. The LCI is the objective database process in the LCI method that basically quantifies the energy and the raw materials that go into the system and what comes out of it, such as air, water emissions, solid waste to land, or any other releases that could occur within a system boundary. So there I'm going to jump on over to what is called a system boundary. And in the life cycle methodology, these can be gate to gate, cradle to grave, cradle to gate. There's many different boundaries of which you can use, and those would all be defined in this goal definition and scope. From there, from the inventory analysis, we get all those different emissions that come out, and those are characterized in what's called the life cycle impact assessment. And those basically take the emissions and characterize them into different impact categories, like I mentioned in the previous slide: global warming potential, ozone depletion, smog, etc. And I put a very simplistic pictorial system boundary here for biochar. We have the residual, that would be from the cradle. We have the production process, making it into chips, making it into biochar, and then again taking it back to the land base. And this would be called a cradle to grave life cycle inventory. And for the results presented today, the impact assessment results all come from the Tracy methodology, which is applicable to North America standards. Again, when you do the life cycle assessment, you have a reference unit or a functional unit. In this case, our functional unit or reference unit is a metric ton of biochar. Today's results will be a cradle to gate, meaning from collection to the production of the biochar. And the data that goes into it comes from a few different sources, one of them which is all the upstream processes that were used to generate the feedstock going into the biochar machine. And the biochar the biochar machine production runs, again from the Schatz Energy Center, these would be the amount of feedstock in, the biochar out, any energy that was used to produce the biochar, and any outputs in terms of emissions or heat waste that were part of that system. All other data, such as diesel fuel, gasoline, transportation processes, came from the US LCI database, as well as several calculations, were performed to get the data how we needed it in the model. So the LCA system boundary for biochar for today's presentation is a cradle to gate. And I want you to remember these colors. Everything in green is considered feedstock on upstream processes, so all the forestry operations. Anything in orange is the biochar machine itself, its input-outputs. And then over here in purple and blue are two different electricity sources that went into the biochar production system. The system was initially run with a diesel generator using electricity, and then they finally did another run where they used what's called a power pellet, which used a renewable fuel going into it. It actually uses the same feedstock that could go into the biochar machine for the electricity generation. So results will be presented both with the two different types of electricity sourcing. In the forestry operations, there were two distinct pathways that we looked at. One of them is pulp logs versus branches and tops. Pulp logs were actually loaded onto transportation vehicles, taken to what we're calling a bioconversion technology site or at a remote location, to where they were chipped, screened, and ready to go into the biochar machine. Branches and tops were actually ground up at the landing and loaded up, taken to that remote site, screened, and again, those two would be ready to go into the biomass, be the appropriate biomass to go into the biochar production system. And then within the biochar production system, you have an energy source going in, a little bit of propane, and of course, your products that were measured coming out. A little bit about the forestry operations. 5 different locations were looked at, and that included southern Washington, central, western, and southern Oregon, and northern California. And for today's results, we had several of these, what are termed as watershed boundaries, several of them within each of those 5 locations that were averaged. And for today's results, we're only looking at transporting it no greater than 60 minutes to this remote location site where it will be converted into the biochar. A little bit about the biochar production system. Again, this was all presented or developed by the Schatz engineers at the Schatz Energy Center. Just a quick recap of how biochar is produced. It is done through a thermal decomposition of the biomass itself in an oxygen-limited environment. Basically, it's a gasification process. The biomass undergoes a pyrolysis within a reactor. The char is separated from the syngas. The syngas goes up, burned in a flare, and then the biochar is collected in these barrels over here. And basically what they were trying to do with their initial test runs were determine if the specifications for the type of feedstock going in, looking at the production rates, the consumption and the production rates of the biochar, what sort of problems and labor requirements that might occur depending upon the type of feedstock going in, how much energy was required to produce the biochar, and then of course any of the hazards, both environmental and fire, that could occur by having one of these machines out in the forest, out in the landing. And again, just a quick recap of that system. We have an electricity source going in, propane, and then the emissions coming out. I'll just jump through that one. I think it's important to spend a little bit of time on the feedstocks within this one. I apologize to the Shops Energy Center. There was a reference here that I think did not get transferred into the final PowerPoint. But all these results that are presented on the feedstocks can be found in the biochar testing report of the Waste to Wisdom team of Task 3. This is pulled directly from their report. So, the engineer down there at the Shops Energy Center did all the work to determine the composition of the feedstock and the biochar. And what I wanted to do was determine if there was any relationship between the different types of feedstocks they used, quality of the feedstock, and environmental impact. So what they determined, and what I took away from their report, was that biochar quality was based on a measurement of percent fixed carbon. They tested 7 different feedstock types, from grounding or chipping different types of conifer to a hardwood to a pinyon juniper. And their general conclusion was that an Lca feedstock criteria for the biochar machine was a moisture content of less than 25% on a wet basis and an ash content of less than 15% as received. And basically, this criteria told them that they could run the feedstock through, they could get limited problems with the machine, they could get a decent quality biochar out, and use the least amount of energy or manpower to get that amount out. So I took that criteria, and that's where I decided to make my first cut in the life cycle assessment model. But after having some discussions with some foresters that developed the forestry data for myself for the LCA model, I thought that maybe I needed to expand upon that criteria a little bit. So first of all, with their criteria, I was able to knock out the juniper because of the high ash content, and I also knocked out the hardwood right away because of the type of forestry operations that I was using in the LCA model. I didn't want to make any other assumptions about that this could be applicable to hardwoods. So from there, that really left me with 3 types of feedstocks to go into it. And each run of the feedstock, I mean, the guys there at the Shops Energy Center ran 2 runs each of each type of feedstock. And for these 3 conifer types, all criteria were met with the low ash content and the low moisture content. Again, small chips also fell into that category. But talking to the folks that provided me with the harvesting data, I asked them what would be the most common chip coming off of the land base with these machines that you're using. And the response was a medium chip. So I go back to the medium chip data and I realize, well, they don't really fall into this moisture content criteria, but to me it's an important feedstock that would come off the land base. So I made a decision to just use one of their runs of the feedstock and eliminate the second run. So data today is based on 5 different types of feedstock inputs, all fitting that criteria of less than 25% moisture content and less than 50% ash. So the results, again, remember those colors, green being the forestry operations, orange the biochar machine production, and the purple being the pallet. So the first results are all based on a metric ton of biochar. And over here on the y-axis is your global warming potential in terms of kilograms of CO2 emitted. These are the greenhouse gases that have been scaled or characterized into CO2. And then on the x-axis, excuse me, I put the percent of fixed carbon and scaled it here accordingly for each of the different types of feedstocks. So, you know, one of the first results that just shouts out at you here is that if you want percent of fixed carbon, or if you even want to call this a higher quality biochar, it comes with an environmental cost to it. That obviously is the highest. These other ones here that take a little bit, have a little bit more soil, take a little bit more work to get processed, lower quality, have a lower environmental. The guys at the Schatz Energy Center actually thought of the ground clean being their baseline for production. It was probably one of their best feedstocks going into it. But again, from a application point of view, probably not the most realistic, taking pulp logs and grinding them. So talking to the forestry guys again, found out that the two probably most common feedstocks coming off the land base would be the medium chip and some sort of combination of tops and bolls that would be ground. So just really looking at those two biochar qualities, we see about a 56% difference in their global warming impact between those two. And again, you see, because of using the power palette, use the renewable resource, the biochar production system only uses a little bit of propane. Most of the greenhouse gas emissions are coming off of the forestry operations with their consumption of diesel and gasoline, lubricants, and the transportation involved in moving the biomass. Want you to take note of the scale here, a little over 300, because all the charts, in order to really display these different phases, I did not scale them equally. So again, the power palette based on metric ton of biochar, a little over 300 is the peak impact. So then I thought, well, if fixed carbon is our metric of quality of biochar, why don't I scale everything, all feedstock types, to a metric ton of fixed carbon? And by doing that, we get a little bit of a flip. We get, at the lower quality biochars, as measured by fixed carbon, you get a higher impact. But what you also get over all feedstocks is you get them a little bit more closer together. So you can say, if you base on a percent of fixed carbon, if that's your goal or a type of standard that you wish to achieve, all of them, with the exception of the ground clean again, which is that base one, all within a reasonable GWP to each other. And again, that difference between those two very common feedstock types got decreased to about a 22% difference. Moving on quickly here to the diesel generator. Again, this is on a metric ton of biochar itself. Probably the most striking difference between this and the power palette is the majority of the impact over each of the feedstock types comes from the diesel generator. So obviously the fossil fuel, as opposed to renewable fuel, have a higher contribution to the GWP. And again, we're looking at 300 at max with the power palette. We're looking at a little over 900 with the diesel generator. And again, those two common feedstocks at about 77%. So again, on a biochar ton basis, higher impact with a higher biochar quality. Again, scaling that to the percent of fixed carbon in the product, you actually get about the same trend as you got with the power palette. But again, the majority of that impact coming from the diesel production. So again, this is all sort of running around the fact of what is the acceptable level of biochar, and then from there you can determine the acceptable impact of which you want to achieve. Also within these results, I did not take it back to the land base. As Debbie had pointed out in her presentation, there is carbon sequestered now in this biochar, so that part is not taken into effect, as well as the trade-off of what we would have done with that residue, such as burning it. Again, that credit is also not reflected in these results. will be in the next analysis of this and in the final report. So some quick, very quick results here. I'm going to start out with the feedstock one, that if we set this criteria of less than 25% wet basis for more reasons than just the efficiency of the machine, if you can get this stuff dried down to 25%, which I think is at a reasonable moisture content to air dry material, you can eliminate a dryer process. These results do not include a dryer because they were able to get it air dried down to an acceptable level. And anytime you add in another process that takes energy, you're adding to your impact of producing that product. So I think it's very important to hold to that and set up a system that can air dry the material down to that 25%. And I think this shows that there is a relationship between impact and biochar quality. And again, if there was some standard for that biochar, what would that be? And what's the acceptable impact of which we're willing to accept in that whole life cycle of biochar. Probably one of the most striking results, and here I scaled them to the same axis, is that we had about a 63 to 70%, depending upon the feedstock, going in by using the power pellet over the diesel generator. So anytime you can use a renewable fuel, you've given yourself a carbon benefit. And does the quality of biochar come with environmental cost? I think we saw that it did. Higher quality, higher impact, but we could actually see that flipped when we based it on a percent fixed carbon basis, where the lower quality came with the higher environmental impact. GWP only here. So setting standards for biochar, percent fixed carbon in it, that would be the driving force, and what level of acceptable impact and feedstock quality are we willing to go for in order to really see that carbon benefit of biochar. Taking this one more level to consider an in-town processing, that was part of the forestry model, and also look at different biochar production systems in relationship to quality of biochar and effort to go into making the biochar. Oh, and so now I'd like to turn this over to Ed, who is going to give us the economics of this production process. So we'll give a couple seconds here to change over microphones.
Okay. This is Ted Bielik. I want to talk about the economics now of biochar production. We started off with a system, a small-scale system producing only about 75 kg per hour of biochar. The system that I took a look at, I did include a dryer, although I built a model that I built a cash flow model that you can add or subtract pieces of capital equipment very easily, and I'll talk about that a little bit more. The system can be operated by just one person, and that is important. Essentially, we're drying the biomass with waste heat and providing electricity with the gasifier genset. This power pallet gasifier genset is a very nice size to power the biochar machine and also a belt dryer if needed, or some small auxiliary equipment. This is a bit of an attempt at an economist's humor. I took a look and said, oh, those must be ladder fuels. In reality, though, the Schatz Energy Center guys took that caption out. An important thing to note on this picture is the big area around the biochar machine that does not have any vegetation on it. That is worth noting. If you are going to set up one of these machines in a forest, it does require a fairly large footprint simply to provide a defensive space in case of sparks coming out. You don't want to add to forest fire danger. I want to talk a little bit about the system. I've done that already, the analysis methodology, some results, and then some conclusions. What do you use to make biochar? Well, preferably a feedstock without much variation in it. The more uniform the feedstock, the nicer the feedstock, the better the biochar that you're going to be getting out of the system. There were essentially two systems that produce very nice biochar-ready feedstock that we looked at. One was a sawdust machine made by Beaver, Korea. The other one was a Peterson microchipper. Because the Peterson microchipper, because microchippers are more common in the U.S., I'm using as a feedstock cost the cost of the chips coming out of the Peterson microchipper, which is $13.12 per bone dry ton. Some production assumptions. There were two systems that we looked at. One was a small system, $250,000 system. That was a demonstration scale. The other one was a commercial scale system, a $400,000 system. In addition to those, we had $45,000 allocated for the dryer, which may not be needed if you can air dry the material. The total system cost came up to $489,500. That was allowing for some construction, some movement of the machines, getting it set up in place, site prep, doing test runs, and so on. 10-year economic life, 20% salvage value. The two feedstock throughputs compare the demonstration unit and the commercial scale unit. Two different conversion rates from the demonstration scale and the commercial scale. We assumed 80% productivity, or about 2,500 hours per year, and then that Peterson microchip feedstock cost. Other important considerations, the power supply from the power pallet, a loader cost that I calculated at $22.57 per scheduled hour. That was just a cost with no labor. There was no labor because I assumed that one person could operate this entire system, and the laborer's cost is incorporated into the cash flow model. I assumed a 10% discount rate, $2,000 per bone dry ton product value that I'll talk about later. Tax losses are recognized immediately, not carried forward or lost, 40% loan, and at 6 years. I use discounted cash flow analysis to analyze the machines. I don't expect you guys to look at all of these assumptions. They are there simply to give you a feeling for the number of variables that can be changed and tested in the model. in terms of the results, which is, I think, what you're primarily interested in, on the demonstration scale machine, for-profit biochar production at a demonstration scale doesn't look very economic. It doesn't look good without additional operating or additional capital or operating subsidies. The break-even product values on these summary financial measures, these break-even product values are the different prices per ton at which the associated net present values before finance and tax, before tax or after tax, at which those net present values become zero. In other words, you are making exactly your alternative rate of return. The break-even feedstock costs are the costs or subsidies at which the net present values are equal to zero. In other words, instead of the specified feedstock cost at $13.12 per bone dry ton or whatever I'd had, if you had a feedstock cost of $62 per green ton, you would exactly break even. In other words, your net present value would be zero before finance and tax. The other piece of important information in the summary financial information is the medium-term and short-term break-even product values. In other words, you would have to achieve $2,171 per ton before tax for your biochar in order to break even over the medium term. In other words, over the next year, you could make all of your variable operating costs and fixed operating costs, but you would not recover any of your capital costs. Over the short term, you would recover all of your variable costs, but you would not recover any of your fixed operating costs. Now, for the commercial scale plant, things are a little bit different. The net present values are positive, and the nominal internal rates of return are all above the discount rates. Break-even product values are below the target price of $2,000 per bone dry ton. The feedstock prices are all positive. In other words, you can afford to pay for your feedstocks. You don't have to get tipping fees in order to make this facility break even. Looking at the costs of this facility, the breakdown, most of the costs, 64.2%, are in terms of variable costs. Of those variable costs, the labor cost is 30.8%. The labor cost is a big portion of the variable costs. In other words, this says that if you can do anything to reduce the labor cost or alternatively increase the output of the plant without increasing the labor cost, you will be more effective. The other variable operating costs, a big portion of that is the machine rate cost on the loader for the system. In a simple sensitivity analysis, the internal rate of return is highly sensitive on the positive side to product revenue. As product revenue increases, the IRR goes up. it is more sensitive to variable operating costs on the negative side than it is to either capital costs or fixed operating costs. The standard operating day that we were working with in the plant, for the plant, was 8 hours. That included about 2 hours of time for both, 2 hours of time for startup and shutdown. So in other words, you had about 6 hours a day of actually producing biochar. Now, if you could increase this operating day, you'd still only have 2 hours of startup and shutdown time. So if you could increase the operating day, your net present value, a simple analysis says that your net present value is going to increase. Something to be aware of in this sensitivity analysis, though, is that associated maintenance costs are not adjusted, and it is entirely possible that in order to get a worker onto that second shift or third shift, you may have to pay more in wages, which those increased wages are not incorporated here. In the cash flow analysis, you can change your project planning life, and the net present value changes depending on the project planning life. I wanted to include this graph just to show you the reason that it goes around like this is because the assumed life, the assumed economic life on the biochar machine, I entered at 10 years. So in year 11, you're going to have to replace the biochar. There is an assumption built in here that there is a replacement of the biochar machine at year 11. Of course, those economic lives can be changed, or you can make other assumptions about, say, major rebuild costs occurring in specific years. That will change the projected net present value profile depending on how long you plan on operating the equipment. There are other economic drivers to consider if you are considering biochar manufacture. One is just the cost to pile burn, which could be $150 to $850 an acre, possibly more. Another factor could be the torrefied product, or the value of torrefied product, maybe $200 to $250 per ton delivered, or could be what the value of the biomass would be in other energy markets. In terms of markets, the primary market for biochar is in soils, but there is a need to match biochars to crops and soil types. There is a need to figure out where the highest values can be achieved from the biochar. In other markets, in addition to direct soils and soils remediation, would be in composting, growing media, but other bio-based materials, wastes, can also be made into biochar. Those wastes could be a competition or possibly a complement for forest resources. There is a chicken and egg issue with respect to biochar's cost effectiveness. If we don't know how effective biochar is, then applied to the land, then that can lead to financing issues. Banks will be reluctant to lend money, which can limit scale economies. there's also a possible issue of the value of biochar in carbon sequestration, but we are not receiving cash compensation for that right now. General conclusions from this are that small near inwoods biochar production may make economic sense. The costs are high, labor's a big portion of it. The costs as presented could be lowered by perhaps using slightly larger units, by perhaps extending the length of the operating day. Biochar itself is a very high value product. It can be used to concentrate biomass value to facilitate more cost-effective transport. The final conclusion, of course, is that more research on this is both on markets, on the biochar itself, and where it can be most effectively applied. More research is needed. And that's all I've got.
Thank you, Ted. Hey, really appreciate that presentation along with Debbie's and Maureen's. I think what I'm going to do is we didn't have many questions come in. If you do have a question, please feel free to put that in the Q&A box at the very bottom. We did have one question, and Han, I know I was going to let you handle Q&A here, but with the one question here, I think I can ask Ted this, and we'll let him answer. This is a question. Says that you mentioned the biochar machine requires a fairly large footprint in order to mitigate fire risk to surrounding forests. And what is the approximate footprint the machinery requires, and what's the actual footprint size since it was near a forest? So I'm going to let you, if you're welcome to unmute yourself, I'll let you answer that.
Okay. I'm not sure. I'm hoping I'm unmuted now. The quick answer there is thank you for asking the question. First of all, it's a very good question. I am not the appropriate person to answer that because I was not running the machine on the forest. This was a bit of information that was mentioned by the good folks at the Schatz Energy Center. So I am hopeful that Han could perhaps answer that, or maybe Andy could answer that, because they were some of the guys who were working with the machine itself.
Hi, this is a few of us from the Schatz Energy Research Center. When we used the machine, we had about 100 feet defensible space around it. That seems to be about the right size, just on each edge of the system.
Thank you, Mark. I really appreciate that. And we've got another question come in that just came in. Han, I might actually hand this over to you. We'll see if I've got quite a few questions coming in here. So Han, I'm going to hand this over to you. I'll let you moderate this a bit and send it out to the appropriate people. And presenters, when Han reaches out to you, you can just unmute yourself and chime in whenever needed. So Han, I'm going to let you go ahead and take over here.
Hello, this is Han. I'm Han. I'm a faculty at Humboldt State University. I'm also the principal investigator of this waste to wisdom project. So I'm happy to moderate the session. We have only a few minutes here. So I am getting the questions from other people here. That the Kathy Minor saying, I did not notice a hardwood conifer mix in your research. Do you have any figures regarding this mix? So I guess Debbie, I guess the Maureen, you've been mentioning about all different feedstock types for your life cycle analysis. Can you answer that?
Yeah, I basically took what was run through the machine in their trial runs, and no, there was not a conifer hardwood mix in there. And I'm not sure from the harvesting standpoint, from those 5 locations, if they're bringing out any hardwoods in that either. That would have to be a question for one of the foresters, which I don't know if any of them are on the panel here today. So no, I just flat out, there is not a mix of that. We could make some hypothetical assumptions, you know, averaging the conifer and averaging a hardwood together, but I don't know what that would really mean. The guys from Schatz Energy Center might be able to say that, no, you can't just do that with the efficiency of the machine.
Yeah, I can also kind of follow up on that. You know, here in the Western United States, we have a lot more dominant species with conifer stand. So there was not much. There was a little emphasis on the hardwood species or mixed. But certainly we have some conifer the hardwood species. For example, here in the Humboldt, we have a panel, some of the hardwood components, but we didn't do much about the mixed components of the species. So next question I see that is about I guess for the Debbie, the increase of the residue stand with the biochar application. Can you answer that question?
Yes. Am I unmuted?
Yeah.
Okay. So yeah, so you know, one of the reasons we thin forest stands is to get the residual trees to grow better, and so we do see trees grow better just by thinning. But depending on the stand age, we also see that biochar can increase the growth of the residual stand as well. You know, like I said, it depends on stand age, but it also depends on the soil type, and we see much better results on coarse textured soils than on fine textured soils. Okay,
thanks, Debbie. The next question is about can we use a low tech as far as the operation of the biochar production, the low tech and high labor such as flame cup or TFOD systems. Well, I'm not familiar with the TFOD systems, but I think that there is the opportunity for modification of our operation system of the biochar production, and so yes, it can be. I guess the lower the labor cost is the significant components in economic analysis. So that needs to be considered. Next question, I would say, Debbie, I'm going back to you. How do you apply biochar in the skid sprayer and the landings?
Oh, good question. So, so we developed a biochar spreader for forest sites, hooked onto a log forwarder and can work on slopes up to 35%. It's really just a modified felt spreader that we've been able to use pretty effectively, and we can you know, you can dial in how much per acre you'd like to apply of biochar. We don't mix it in. I think that was the second part of that question. On forest sites, because we know that the forest floor is extraordinarily valuable for cycling nutrients, we just put the biochar on top, and you know, usually within one winter, most of the biochar has worked through the forest floor and into the mineral soil.
Yeah, okay. Next question about the spontaneous combustion of the biochar, things that is stored. Mark, I'd like to ask you, do we have an issue with the spontaneous combustion with the biochar piled and stored?
Yes, when the biochar comes out of the machine, this machine had a cooling auger to basically cool it with an external water jacket so that it would it would be collected into metal drums at a lower temperature. We would measure the temperature on its way out, and if it wasn't cool enough, we would add some water to it just to cool it down. But if biochar is produced and then not cooled down afterwards to an appropriate temperature, then there can be issues with combustion. But once you get it down below, 100 or 80 degrees C, it shouldn't be an issue anymore. So that should just be incorporated into the design of different machines.
Okay, next question is for Ted. It looks like it's about 11 o'clock Pacific time here, but I'm going to go over a few more minutes to answer the few questions we have. So the mobile setup, cost of the setting up and breakdown and moving, has that been all that cost components included in your financial analysis? Ted? Okay, if the Ted is offline right now, but what I can tell you, yes, it's been included, those cost components of the included in our financial analysis. That will be more explicitly presented in our next webinar, which will be scheduled for September. So please stay with us, and so there will be another the biochar. Another webinar scheduled for next month, and then we will talk more about the financial components of the different pathway of the production system. And the next question, Dave Atkins asked about how did you come up with the market value of $2,000 per ton? Ted, are you still offline?
Can you hear me?
Yes, I can hear you now. Go ahead.
Thank you for that question. The $2,000 a ton first was a ballpark sort of figure that was given to us by our partners at Biochar Solutions. In looking at some market prices, though, the International Biochar Initiative came out with a document called the State of the Biochar Industry in 2014. They had prices in dollars per pound that I converted to per ton prices for both pure biochar and blended biochar at the wholesale level and at the retail level. At the wholesale level, the pure biochar sold for $1,361 per ton. So that $2,000 a ton is way high. That $2,000 a ton that I was using was way high for that. At a retail level, pure biochar was selling for $3,865 per ton. This was there was a sample of 28 that were providing information. So that, again, that $2,000 a ton that I was using is a bit low. So that $2,000 a ton you could think of it as kind of a blended ballpark target price somewhere between a pure wholesale and a pure retail price. I hope that answers the question.
Okay, thanks, Ted. So another question for Debbie. Can the biochar reduce the pH level of the soil after land clearing?
It depends on the biochar. Most biochar is usually about, at least from woody feedstock, most biochar is about 7 to 7.5 for pH. And so, depending on the soil and the biochar, yes, it can reduce the pH. Other places it's been used to increase pH, kind of like liming wood. And so it just depends on the feedstock and the kind of biochar that you produce.
Okay, thank you. The next question for the marine. what is the difference in the effect of the global warming between open burning versus the biochar production and the fire, forest fire? Have you done anything like that?
Not yet. Well, not presented here, and I couldn't give you a number. Certainly have looked at pile burning. Could even bring in broadcast burning, which isn't quite as common here in the Northwest as it was in the past. Forest fires, I think I need to pass the buck on that. I believe maybe it's going to be included in our impact air quality indicators that are part of this project. I don't know. But yes, in the final report of the Lca of Biochar, business as usual would be to the pile and burn, and that will be put in the analysis. So there would be a number given to that.
Okay. Next question was the final, the product quality of the biochar compared to the chip quality. So I got some of the answers from the Schatz Energy Center here at Humboldt State University that dirtier chips with the higher ash content will result in the biochar with more ash, and this can be bad or good depending on the exact minerals available in the ash and the impact on soil. So that was the answer we got from the Schatz Energy Center. Thank you. Next question is, how would Ponderosa pine slash with the needle rate as biochar quality? Let's see. Mark, do you think you have any answer to that question?
It's similar to the answer to the previous question, just on the effect that ash would have on the final product. Our testing basically just showed that as long as the ash content is below 15%, then this particular machine can process the material well, and then it's just a matter of what are the exact minerals in ash, I think, and if they're good or bad for soil. The next question here is a top bed, open draft, or even burn pile management. I'm not quite clear about that question, so I'm probably going to skip that for now, and you are welcome to ask us the question back again. Did you spread the biochar on the surface or incorporate into the soil, Debbie?
Yeah, here we go. So it depends on the site. On forest sites, we just put it on the soil surface, but on rangeland and mine sites, we can incorporate it unless the soil is too rocky. But usually, most soils that we've worked on have been pretty coarse textured, and so the biochar readily moves into the soil over time.
Okay. Next question is for Ted. Here's about economic analysis again. Here, what do you recognize as the most cost-effective feedstock and the final product transportation method and conditions?
The most cost-effective feedstock. It's a difficult question because ultimately the most cost-effective feedstock is going to depend in part on what the requirements of the customer are. If the customer is wanting a uniform, nice product, then the most cost-effective feedstock is going to be the one that can produce the uniform, nice product at the lowest cost. Realistically speaking, that might well be agricultural wastes. They would be the first products that you would look for depending on market size. For example, walnut shells would make a wonderful feedstock for biochar. If as markets for biochar grow, then microchips from forest waste are going to be a very, very good feedstock. So I'm sorry I can't give you a definitive answer, but as an economist, I guess you should expect that my answer will be, it depends.
Thanks, Ted. Well, I'm the guy, the team member here in the Waste to Wisdom, looking at some of the logistics of the hauling the raw material to the conversion site, and also the hauling the products to the market. So we have been looking at many different some options of the transportation for hauling the raw material and as well as the products. So probably we are going to present a lot more information in the next webinar. So please come back to our next webinar on that. And to make a short here, the hauling the raw material, we probably use the regular logging truck or the hay rack, the kind of raw material, the transportation that is readily available today to haul from harvested site to the biomass conversion site. And for hauling the material, the products, the torrefaction, torrefied wood chips, and the biochar and briquettes, depending on the product material, so you have a different transportation, machine and trucks that can be nicely fit for those different products. So we can talk a little more about it and in our next webinar. I guess it's time's up. I think we have addressed all the questions. Time's up. Thanks for the staying with us, even the 12 minutes after 11 Pacific time. So if you do have more questions about anything about our Waste to Wisdom project and the webinar information presented today, please contact directly to those presenters at their email showing in this slide. And also, you are welcome to contact our Waste to Wisdom team members through our Waste to Wisdom website. So that's it for now, and thanks for joining us again. Thank you. Bye.